All right, good morning and afternoon, students. I want to take a few moments to begin our information from the textbook, talking about liquids, solids, and gases. As you see, this is going to be taken from really two different chapters that we're going to cover, so I need you to stick with me. Make sure you're filling out your guided notes as we continue on. Now, let's go ahead and introduce to you what our learning goals are, our objectives will be for this coming unit, or part of the unit, I'll say. Now, students will be able to, by the end of this unit, identify three types of intermolecular forces, differentiate between the types of molecules with which those intermolecular forces react, explain the three assumptions of the kinetic molecular theory, the function of a barometer, how pressure is determined, convert between the different units of pressure, and last but not least, explain how temperature is related to the kinetic energy of particles. This seems like a lot of information, but stick with me, and we should be able to do this. And again, if you need, make sure that you rewind or fast forward as needed to finish off and make sure you have the information written down. Also, go ahead and rank yourself on this information. Where do you feel like you are? My goal is by the end of this that we can move you up a little bit more into your understanding, and then the activities in class will sort of help out a little bit more. Now, intermolecular forces. These are going to be the attractive forces that actually hold two or more molecules together. We talked about this earlier in the year when we talked about covalent bonding, and we used water as a prime example. There are three main examples that we're actually going to utilize. First, we have hydrogen bonding. The second one is London dispersion forces, and the third being dipole-dipole forces. Starting off with hydrogen bonding, this is going to be the strongest of the intermolecular forces. Now, all three of these forces that are given to you are actually fairly weak, but in terms of strength, hydrogen bonding is actually going to be the stronger of the three. Now, hydrogen bonding is going to occur between the hydrogen of one molecule and a highly electronegative atom of another molecule. For example, if I have, a hydrogen bonding to an oxygen, a nitrogen, or a fluorine. These are examples of very highly electronegative atoms. We're going to usually see this happen for hydrogen bonding. Now, the second one that we now bring into the place is London dispersion forces, or sometimes you'll just hear it called dispersion forces. These are going to be on the opposite end of the spectrum. These are going to be very, very weak interactions, and they're going to be caused by just the movement of electrons. One of the things that we'll note throughout this unit is electrons move in a very random pattern. There's no set, they must go here, route they must face. Now, London dispersion forces, or LDFs, usually occur in nonpolar molecules due to random electron movement. So there's usually no interaction if we think of something that is nonpolar. It doesn't have a charge on either side of it. But because the electrons are moving in the way that they do, it creates an instantaneous charge, or a charge that lasts for maybe a split second or so. Now, the larger the molecule, the stronger the London dispersion forces will be. And the last but not least, we have dipole-dipole forces, which occur between two polar molecules. Realize I have a typo there. I'll fix that a little bit later. Now, with these molecules moving about, we had to come up with a way to try to explain how they're going to interact. And we're going to spend a lot of time throughout this unit talking about gases especially. But once we figured out, this is what seems to be happening, we had to come up with a way to understand these interactions. So what's been developed is what's called the kinetic molecular theory of gases. With this, there are going to be three main assumptions that are accepted. First assumption, particles in a gas are considered to be small, hard spheres with insignificant volume, meaning there's not going to be really much change between the size of the molecules. Also, the motion of the particles in the gas is rapid, constant, and random. gas molecules, they're interacting with each other, they're bouncing off of each other, they're bouncing off of the things around them, but there are no set patterns. So if it hits at one angle, it'll go completely random in another direction. Also, last but not least, all collisions between particles are perfectly elastic. As we talked about in our previous unit for thermochemistry and for kinetics, we talked about the fact that as these molecules bump into each other, they actually tend to transfer a little bit of energy. What we're saying is when we say they're perfectly elastic, when they interact, when they bump into each other, they collide, there is no change in energy. They just bounce right off and continue on going. Using this information, we then go into a few other examples. Now, this is to sort of explain what we just talked about in the previous example. First, in the first picture, you notice that they collide at different points, but as they do, the energy is just transferred. It just continues going the same way. In part B, we see that even with one gas molecule, that it moves in straight lines from each collision, but it is no set pattern around the box. And last but not least, again, that the first assumption that we dealt with being that there is no difference to the molecule size or shape. Now, how does this explain gas pressure? The term pressure comes from the formula for force per unit area. So the more collisions on a specific area of space means the more pressure that's exerted by the gas, the more collisions that we have in those certain spaces. Now, when we think of atmospheric pressure, this is what we usually talk about when they say you're at sea level or below sea level or above sea level. This is going to be the pressure that's exerted by molecules in the air on just different matter on the Earth based on where the location and the elevation of that area. How we measure this is going to actually be called, we use a tool called a barometer. The higher the mercury is pushed up into the column, the higher the atmospheric pressure is pushing down on the mercury inside the pan. The unit that we're going to utilize for this is called the Pascal, or the way to express it in terms of physics, be 1 Newton per meter squared. Other units that we're going to get very comfortable with using is 1 atmosphere, 760 millimeters mercury, and 101.3 kilopascals. These are going to be the units that we use throughout this time as we talk about pressure to try to explain what's going on. Now, this is an example of a barometer. We have at sea level, you see that there's more pressure pushing down on the mercury here. So because we have more pressure on the mercury, we have a higher volume here. But with less pressure, we stop a little bit less, just shorter. And this will be the difference in elevation. This will be how we determine how long you need to cook things for based on the boiling point, which we're going to get to in just a second. It'll also help us to understand how we need to inflate, or if, again, going into business, we'd have to figure out how to make products that would be able to function the same at each level. Now, how are kinetic energy and temperature related? One of the discoveries that we have from 1848 comes from a man named William Thomson, or as he's known, Lord Kelvin, who observed that by observing Boyle's gas law, he looked at a point and saw that when the temperature reaches a certain point, not Boyle's law, this is Gay-Lussac's law. He looked at the fact that at a certain temperature, it seems like the volume completely disappears. Well, we know that we can't just have matter disappear, so what had to have happened at that point is the molecules would have to have slowed down so much that the volume cannot be detected. Using this understanding of kinetic energy, he wrote an absolute scale, or he created an absolute scale that we use to this day. And it just says that at negative 273.15 degrees Celsius, or 0 degrees Kelvin, this will be the point that the molecules stop moving. So the lower the temperature, the slower the molecules will move. The higher the temperature, the faster the molecules will move. We'll have to convert back and forth a good amount between Kelvin and Celsius, because all of our gas law calculations will have to be done in Kelvin. This is just to show what happens at higher temperatures in terms of the number of molecules that are actually performing or moving at the rate at which we need them. Now, go ahead and take some time. Again, rewind if you need, and we'll continue this in class when you come in. Have a great day. Also, make sure you bring your questions so we can get things clarified. Have a great afternoon, and I'll see you in class.